Assalamualaikum and good day to everyone. So today our group decide to present to you guys about our group assignment MAT183 calculus. So next, these are our group members: DANI bin Rahim, HAZIQ bin ANUAR, Muhammad AQIEF ZUHAER bin ZANIMAN, and me myself Azanif bin ZAKARIA. So before we start, I would like to acknowledge that we are deeply appreciative because we successfully completed this challenging project within the deadline set by our mentor, Madam Norzila. This achievement would not have been possible without the incredible teamwork and dedication of our group members, AFIQ, HAZIQ, AQIEF, and Adam. We also extend our heartfelt gratitude to our mentor, Madam Norzila, for her invaluable support and guidance throughout this semester and this project. So, our group project is about application of differentiation. Introduction. In differential calculus, related rates problems involves two or more variables that change at the same time, possibly at different rates. Also, the rate of change is usually with respect to time. Definition of related rates. Related rates and problems involving related rates take advantage of quantities that are related to each other. Related rates help us to determine how fast or how slow a certain quantity is changing using the rate of change of the second quantity.
Assalamualaikum, my name is Muhammad AQIEF ZUHAER and my matrix number is 2024, 573 and 533. I'm going to explain the technique to solve differentiation problem. There are three techniques to solve differentiation problem. First one, we have derivative of sum and difference. The second one, we have a derivative of a product function, which is product rule. The product rule is used when taking the derivative of a product of two functions. Next, we have a derivative of a rational function, quotient rule. The quotient rule is used to differentiate a function that is the ratio of two functions. Let's look up at the problem statement. So this is the question. A closed cylindrical container of radius, which is RCM, and height, which is HCM, to be made to hold a 600 cm cube of liquid. We're going to answer the first question first. Show that the surface area of the container is 2 pi r square plus 1200 over r. Next, we're going to find the value of r and h that minimize the total surface area of the container. Hence, find the minimum surface area of the container. Let's look up the first question. This is our first question. We have r, which is the radius of the cylinder. H is the height of the cylinder, while pi is a mathematical constant approximately equal to 3.14. Firstly, here is an area equation. We have 2 pi r square plus 2 pi r h. Next, we have the equation of a volume, which is pi r square h. Now, since we know the volume of the container is 600 cm cube, we can use the formula, the volume formula, to express h in terms of r. Now we're gonna include the h. So now we get the h equals to 600 over pi r square. Then we need to plug in the h value to the equation area. After that, we're gonna get rid of r. Then this is the final answer. To minimize the material used in constructing a closed cylindrical container to hold 600 cm cube of liquid, we need to minimize its surface area by utilizing the formulas for the volume and surface area of a cylinder, and expressing the height, which is h, in terms of the radius using the volume constraint. We can derive the surface area of the container as 2 pi r square plus 1200 over r. This expression represents the relationship between the surface area and the radius of the cylinder.
Assalamualaikum, my name is KHAIRUL and I will present for the question 2. So for this problem, we are tasked with finding the values of R, which is radius, and H, which is height, that minimize the total surface area of a container. Let's go step by step to understand how to solve this optimization problem. The total surface area A is given by the equation A, which is 2 pi r squared plus 1200 over r. Here, 2 pi r represents the area of the two circular ends of the container, and 1200 over r is related to the side of the container. To make it easier to differentiate later, we rewrite the formula in a different form by expressing 1 over r as r to the power of negative 1. Now, we need to differentiate A with respect to R to find the critical points where the surface area may be minimized. Using the power rule for derivatives, we calculate the area equation. Then, with this derivative represents the rate of change of the surface area with respect to the radius. In the next step, we will set dA over dr equals to 0 to find the critical points. After finding these points, we will determine whether they minimize the surface area using the second derivative test. After equating the derivative to 0, we multiply through by r squared to eliminate the fraction. Then, we rearrange the equation to isolate r cubed. Finally, take the root to solve for r. At this stage, we have found the radius r that minimizes the total surface area of the container to be approximately 4.57 cm.
So, Assalamualaikum, back with me again. So, in this step, we aim to verify that the given radius minimize the surface area of the object using the second derivative test. So now, let's break it down step by step. First, the relationship between the height, radius, and volume is given by h equals to 600 over pi r squared. So by substituting r equals to 4.57, we perform the calculation and we get the height. So step 4. So this is the first derivative test. dA dr equals to 4 pi r minus 1200 r to the power of negative 2. The step below is, it represents the second derivative to confirm whether the critical point minimize or maximize the surface area. Again, we substitute r equals to 4.57 into the second derivative test. We get 37.71, which is greater than 0. So, since it is greater than 0, the second derivative is positive. This confirms that the critical point at r equals to 4.57 is corresponds to a minimum surface area. We can conclude that it is greater than 0, so it will minimize the area.
Assalamualaikum. My name is Adam Dani Rahim. My matrix ID is 202-452-5571 from group RCDCS 1102B. So today I will present my slide about the minimum surface area of the container. So I will continue my slide after AFIQ, as you can see the video before. Okay, so for the step 1 is we are given, we already have a formula that we got. We are using the formula we got from before. This is formula, the total surface area of cylinder that we use to find minimum surface area of the container. So for the next step is, secondly, as you can see here, we need to insert the value of r that we got from before. I think from HAZIQ video, we got the r is 4.57. So after we insert the value of r, we calculate to get this answer, final answer. As you can see here, this is the final answer that we calculate is 393.81 cm power of 2. So let's go to the next step. For our next slide. So this is our conclusion. By expressing the height of the cylinder in terms of its radius using the fixed volume of 600 cm power of 3, after you got the value of h, the surface area of the cylinder container is simplified to the formula. As you can see here, this is our formula that we used before. Using the formula you got, you need to find the value of R and put the value of R to get the surface area of the container. Yeah, that's our conclusion for this question for our project. So let's go to the next slide. This is our reference. We are using this video to get our question, and we learn from this video also to make our question. I think that's all from us. Thank you.